Welcome to the first episode of The Edge of Science. In today's episode, we are going to talk about stars. How do they born? What happens to them after they die? And how much energy do they release during their lifetime? Today's guest is Kristyn Brandenburg. She's a graduate student at Nuclear Physics Institute at Ohio University, and she works on the nuclear physics of the stars. Glad to have you here, Kristyn. How are you doing?
Yeah, pretty good. Thank you, Reza. I appreciate you having me.
So let's just jump right into it. Can you, in simple terms, explain to us what have you been doing during past couple of years?
Sure. So I'm entering my 6th year of graduate school. I've been at Ohio University working under the expertise of Zach Meisel. He's one of the professors here. And throughout my time, I've taken classes as a grad student. I've taught labs. But for the last, I'd say 4 years, I've been heavily into research. So my job as a researcher was to design a detector that we will use at the particle accelerator here on the Ohio University campus. So we're incredibly lucky to have a particle accelerator right there for us to use. I got to learn how to operate the accelerator, help out with other experiments, and then really, get into the heart of what I did was design this neutron detector that we would use for experiments at the lab. And in the last year, we actually got it up and running, and we've been doing experiments with it, which has been awesome. Kind of a dream come true for me to get to work at a place like this, and then to get to partake in experiments and do that kind of thing. So it's been an awesome couple of years.
Just a background for the listeners. I know Kristyn because I was also a Ph.D. student at Ohio University, and I graduated from there a year ago. And she gave me a cool actually demo in the lab and took me around back then. I remember very, very well. It's a very big lab for
we do tours all the time, by the way. So if new students that come, or they'll have various kind of big wigs from other labs, or maybe the Ohio University president, for example, might stop by and want to hear about what we're doing, and the feedback that we get is always really good, which is awesome, because science sometimes gets kind of a bad rap, I guess, as being boring or something like that. But people love to come, and I am so thankful that I get to show them around and hopefully get people excited in science.
I mean, who shouldn't be excited to see a gigantic experimental machine at work? You can't see that at anywhere else, right?
Yeah, that's how I think about it. So
that's awesome. So I know that in your research, you heavily work on nuclear physics and interactions that actually are related to stars in the universe. Yep. Now, I just want to, for the listeners, give us some background information so we can get to actual research you're doing, which I think we need some background info for that. So first thing first, how do the stars form? What happens to these gas clouds in the galaxies, these cold gas clouds that they turn to a star?
Okay, yeah. So I will just give a caveat that I'm primarily a nuclear physicist who does reactions because we're interested in stars. So this is going to be how stars work from a nuclear physicist standpoint. But basically, I would say that that the universe was formed in the Big Bang. Several billion years ago, matter expanded because of gravity. You get certain clusters of higher density, and those things can form stars eventually. There are nuclear reactions going on that power these stars. And over the course of millions or billions of years, these reactions keep building up. You power stars, and you end up seeing what we see today when we look out into the sky, which are just these little bright dots. But it turns out that there are billions of stars, billions of galaxies, and there are nuclear processes going on in all of them. Which is
let me get in a bit more into the process when the star starts actually transferring heat outside, right?
Okay.
So at the beginning, we know the gas cloud, the gravitational force starts pushing the gas down and down. And then when a certain threshold is passed, there's something happening that this gas turns to a star.
Yep.
In that moment, I think nuclear physics becomes very important.
Because, that's a good point.
Because you go ahead.
Oh, sure. Sorry. So at some point you just have this nebula, which is just this giant gas cloud full of, we'll say, stuff. And because of gravity, that stuff will start to come together. And at a certain point, you have enough pressure built up inside of this gas ball that the molecules or the elements that are, traveling in and out of that gas cloud will start to hit each other. And when they hit each other, if they have enough energy, they can do reactions. So maybe you have protons hitting another proton, and you'll form another element. And then those can go on to do that over and over and over and over and over. And that's what keeps the star from collapsing in on itself, is that you have, gravity pulling everything in, but you also have these reactions going out that are pushing it out. And so you kind of get this equilibrium, and that'll last for a while, but eventually you can run out of fuel, and that's when things kind of go crazy.
Yeah.
Yeah.
So, regarding the nuclear physics part, just for our listeners, how much, the comparison between the scale of the energy when this explosions start happening, how much energy are we talking about compared to the Earth?
It's a lot. So for my stuff, we deal on the order of millions of electron volts. You can think about things in terms of joules, or maybe a better example is, so when a star goes supernovae, you will see the brightness of that supernova outshine everything near it. So all of the rest of the stars, all of the rest of the galaxies, you will see just that one star that's gone supernova in your telescope. And that is pretty wild, actually. Another way of thinking about it is, so if you think about fission, 1 gram of uranium that fissions is going to produce enough energy, or roughly the same amount of energy, as 3 tons of coal. So if you're thinking about different energy sources, you could consider, just this 1 gram compared to 3 tons of coal.
Yeah, so that's a lot of energy is going on there.
Yeah,
now, so we know that the stars are born and you said it gets to equilibrium because there's this gravity that's trying to collapse the star. Mm-hmm. There's the nuclear interactions that are pushing out, and that's how you get the heat that you see on Earth. Let's say even look at the sun, because sun is another star as well. Mm-hmm. And sun has those nuclear interactions, right? Now, how long does a star live? What's the lifetime?
It depends. So mostly it depends on the mass. So we would normally say something is a lower mass star or a higher mass star. And for the first part of their life, they're going to live about the same. But at a certain point, they'll take different trajectories. So lower mass stars, we're talking on the order of, basically our sun or lower, I would say. They will live their life. They will go through reactions like fusing hydrogen to form helium. Eventually, they'll fuse more helium to form elements like carbon and oxygen. And at a certain point, they will run out of their fuel, and they will expand their outer layers, leaving behind just this brown dwarf. And that dwarf star will live for basically the rest of its life, because it doesn't have enough energy anymore to do any more reactions, and so you won't basically see it like you would see the star before.
So I know, for example, our sun, right? It lives around 12 billion years, if I am not mistaken.
That sounds reasonable. That the Earth is something like 4.5 billion, and the stars, or our sun, has been here longer than that. So
ish, I think we go for 12 billion, right? And then when the sun, so basically since when it gets larger, the larger stars, I know that they tend to die earlier, right? Mm-hmm. And why is that? Like, why when we have a larger star, it dies earlier than a smaller star like our sun? And when it goes smaller than sun, they were gonna last a lot longer, right?
Yeah, that's an interesting point. And it's I think there's a phrase, live fast, die young, which is kind of relatable to these bigger stars. And what it all boils down to is the fact that you have more stuff. So you have more gravitational pull. And so you have more of that pressure inward. And because of that, all of the molecules and the elements are going to be moving faster, and they're just going to burn up their fuel faster. And so the ultimate, end of life is just going to happen faster because you have more stuff.
So now we're getting to a point that we can talk about what happens after they die, right? Because kind of stars are undeads. They never die, right? They transfer to another form. Mm-hmm. So what kind of things happen when a star actually dies right at the moment of death? Let's talk about there first, and then
Yeah.
things get very crazy afterward. I know.
Yeah, I guess it depends on what we're calling its death. So typically, when someone is mentioning the end of a star, we think supernova, right?
Yes.
At a certain point, you've burned up all of the fuel, and so you no longer have that pressure outwards from the nuclear reactions, and then gravity just collapses in on itself, and then you get a shock wave that just explodes everything. And you're left with behind either a neutron star or a black hole. And depending on which one you do, that just depends again on the mass.
So let's say at the moment of death, I know that we have different types of supernova that can happen, right?
Mm-hmm.
Different type of things. But the one that we're talking about is a core collapse right now. When actually one star dies, it's not in a binary, meaning that it is not with another star or something. Mm-hmm. So in the core collapse sense, the amount of energy, let's talk about that. We were talking about it a couple of minutes ago, but mm-hmm. This is one of the highest energy things ever happening in our universe, right?
Yeah.
So just for a context, when we talk about energy, again, how much that energy is, but let's put it in a scale.
Yeah, that's good. For the supernova, I don't know that I have a number. I mean, it's calculable. Do you know off the top of your head what
I think
what that would
it
be?
is around 10 to the power of, I know in ergs. So sun comes to give us 10 to the power of 33-ish ergs per second, I think, energy. I think mm-hmm. supernovas can go up to 10 to the power of 50 at the moment of explosion. So I like this XKCD cartoon that, the amount of dangerous neutrinos, mm-hmm. by the way, we'll talk about neutrinos, when they come to us. If the sun goes supernova, it's like having a hydrogen bomb on your eye, exploding on your eye. That's that much of energy we're talking about, right?
Yep.
So what kind of interactions goes on there, nuclear physics side?
Yep. So this is kind of the heart of what I do and how the nuclear physics ties into supernova and why someone like me would care about them. And that is for origin of the element studies. And what that means is, we all kind of learned about the periodic table when we were in high school, right? You have hydrogen, helium, uranium, all sorts of different elements. And there's a question in our field of, well, where did all of those elements come from? And we already mentioned that, hydrogen's fusing into helium. You can make carbon and oxygen in some of these stars. But up until the point of supernova, there's a limit to the elements that you can make. And that is iron. And it gets a little bit complicated, but basically you can fuse elements together up until you hit iron. At that point, it's no longer energetically favorable, and so they just don't do it. But at the point of supernovae, you get different interactions. You get lots of neutrons, and you can actually start to capture those neutrons, which will allow you to get to heavier and heavier elements. And so during that supernova, there's just so much energy. Those particles are moving so fast that you can start to produce heavier and heavier elements.
So basically, whatever heavy elements we see on Earth, they're actually coming out of, a star's explosions,
for the most part. But it turns out that we know this to be true, but we don't know all of the details. So if I were to say that we know all of the processes that create all of the elements, that would not be true. In particular, there's this region from about zinc to 10, which has protons of about 30 to about 50, that we actually don't know right now where those elements were made or how they were made. There's some idea that they were made during a core collapse supernovae produced by the neutrino-driven wind. But it turns out that not enough nuclear physics has been done to allow us to say if that's true. So when modelers, get on their computer and they make models of stars and stellar explosions, they need a lot of inputs into those models. They need to know how massive the sun is, what the entropy was, what the things like electron fractions. There are a whole bunch of things that go into that. And one entire component is nuclear physics inputs. So things like cross sections or masses of the elements, there's a whole lot of things that go into it. And for these particular elements, the nuclear physics that they need, for the most part, has not been measured yet. And that's a huge problem because when you don't have measurements, you rely on theoretical calculations. And sometimes those theoretical calculations are wrong or uncertain. And so you just need to go out and measure those reactions. So the same reactions that are going on in the stars, we need to do those reactions here on Earth, understand all of them, or hopefully the most important ones at least, and then give those to the modelers who are modeling stellar explosions, and then we can learn something about nature.
Yeah, because as far as I know of from my background, there wasn't any code that could explode a star, right? So they would detonate it on a simulation. They would try to detonate it on their own because there was no process that would explode, so they couldn't get it right.
Yeah, they also do differences between 1D, 2D, and 3D simulations of stars. And for the most part, they rely on 1D simulations, not 3D, because those are just so computationally expensive. So, yeah.
We talked about neutrinos because they're very interesting when you talked about neutrino wind coming out of a supernova, right? The core collapse. So maybe our listeners would not know what's a neutrino, right?
Okay, sure. So neutrinos are almost massless. They do have a little bit of mass, and they barely interact with anything. Someone like me would say that their cross-section for interaction is really low, which just means that for the most part, they just travel right through almost everything. And they can carry a lot of energy away because they're not interacting with the material of the star. So if you have a neutrino at close to the center of the star, for the most part, it's just going to make its way out of the star without interacting with anything, which is pretty wild, actually.
So we know then they don't interact. They're like a ghost, right, in physics.
Yeah, I would say that. Yeah.
And
they do interact, but their probability for doing so is very low.
That's very little interactions. But how do we catch them, basically, on Earth, right? How do we catch or count neutrinos or try to see their properties in the lab?
Yeah, so this is pretty cool. There's, I think it's like the Super Kamiokande detector. And anyway, what they did is because they don't interact hardly at all, that just means that you need a whole lot of stuff for it to potentially interact with. And they got this huge detector. I think they filled it with water, and because neutrinos they're passing through us right now, they're passing through all of the Earth. They set out their detector, this huge thing, and eventually some of those neutrinos will make their way through that detector, and eventually some of them will react, and you can measure that. And you can imagine that it was really hard to do. It took a whole lot of physicists, a whole lot of planning, but eventually they did. And that, I think if I'm remembering right, that experiment led to what was it, the neutrino catastrophe or something like that. And anyway, it was a pretty big experiment, and it was very.
There's two type of this. There's one is in the Japan, as I recall. The other one is in one of the poles under the ice.
It's like snow cap or something like that.
I think so. Yeah. But I remember exactly the neutrinos have to go through a lot of water. The water is, I don't know how much, but it is a pretty big container full of spherical looking golden spheres there. The kind of detectors all around, right? They want to detect everything. Yep. And I have a funny story that one of the professors from California went there to see. I remember Professor Schmidt. He was saying that he saw through the cosmos that Neil deGrasse Tyson is sitting in a boat inside that water. He wanted to go see, and he thought he can go visit there. And he just realized it was a computer simulation.
Oh my God.
And only person who could visit there was the shogun, actually, the emperor of Japan. Nobody else can go in there, literally. So just for listeners' interest, if they want to know how important that experiment is.
Yeah.
So we talked about neutrinos, how the measurements happen. Now, after the star dies, or per se transfers to another form, because they are undeads, right? They don't die. This is just a term that we use. Mm-hmm. What happens? What is left over? We talked about brown dwarfs.
Yep.
but what mass levels do we need to have to get a brown dwarf? Or if we have larger mass, what's going to happen then if it
Yep.
is?
Yeah. So if you're greater than something like 3 solar masses or something like that is left behind, then you will end up as a neutron star. Or greater than that, you will go to a black hole. And it's not all of your mass that ends up as that neutron star or as that black hole. Through that explosion, you actually propel lots of materials out into the universe, and that's the stuff that I'm actually interested in, because when you expel all of that material, at that point you've built up elements potentially to iron, and those get flung into the universe. And as gravity pulls all of that stuff together, you're going to start forming new stars. And at that point, you're not starting a star just with hydrogen, helium, maybe some lithium. Now you're starting a star with hydrogen, maybe some oxygen, maybe some carbon. And so your nuclear processes are going to be different, and then you can create different amounts of different elements. So it's twofold: what is left behind, and then also what was propelled into the nearby universe.
So we know the propelled ones, they carry a lot of elements, as you said. So how do they end up in planets per se? Because that's also interesting, because we live on a planet, right?
Yep.
Not on a star, and we see them.
Yep. So you're going to propel all of that matter, and you form what's called a planetary nebula. It's not necessarily a planet, but it is a nebula. It's sort of like a kind of a misnomer. But basically, it just means you've now got a nebula of gas, and because of gravitational interactions and because those particles are all moving, eventually, similar to what happened to form that first star, you're going to get pockets of higher density, and you're just going to start getting more and more matter, and eventually you might get another star out of it. You might get planets. It just depends on how that matter was distributed and what the conditions were of that place, I'll say.
Yeah. So how heavy can we go on the elements when through the star explosions in our periodic table?
Yeah.
Up to where do you think they come from, stars?
Yeah. So they're let's see. So from the Big Bang, just from the creation of the universe, you've got hydrogen, helium, maybe some traces of lithium. And then through stellar processes, just your, sort of your normal everyday star, you're going to get up to iron. And then past that, you do neutron captures. So you get a neutron, and then you do something called a beta decay. I'll not say much about that. But we call that the S and the R process. And that will basically get you all the way. There's some question about the middle part. There are also fission processes that get you on up the periodic table. But for the most part, that's basically what's going on. And we think some of those heavier elements are created in neutron star mergers or collisions of black holes. That's one of the areas that is a really hot topic. And maybe some of you have heard about the LIGO experiments, where they actually detected gravitational waves. And that's something that people are looking into now to try and figure out, what sort of processes were going on during that time. It's kind of the first data that we have in that area, and it's really exciting. And so we're actively learning about that, which is pretty sweet.
So we talked about neutron star. I want to make sure that people who are listening, if they're not familiar with what a neutron star is,
Okay.
because it has the name neutron star, and so it can be misleading, right? So let's get the story there. Why they are called neutron stars?
Yep. So for the most part, you do have, I don't want to say just neutrons. So neutron stars aren't what I study, so I want to be a little bit careful here. But you do have protons, electrons, neutrons, and the density is just so high. To give you some scale here, you can imagine, packing all of the weight of an entire star into, the span of a single town, which is, almost unfathomable, but that's just how dense they are. And yeah, so your question was just, what is a neutron star?
Yeah, so I think you answered it kind of. When the pressure is too much, the gravitational force is too high, we know that there should be something to hold up to this gravitational force. But in this case, I think it's too high that electrons are bombarding onto the atoms, right? They
Yep.
they interact with protons, and that's what you get. Am
Mhm.
I think
Yep.
I'm
Yeah, I think that's fair.
and they all become neutrons, right? And this is one of the craziest objects in our universe. We don't too much understand what happens in them. There are lots of work going on. Just for people, I wanted to, to understand what neutron star is. It's not fully neutron, by the way. It has a surface of, right, other
Yep.
material.
One thing I can say that I've learned kind of recently through going to conferences and learning more about neutron stars is that my idea of a neutron star was basically just a giant ball of really dense neutrons. And it turns out that they have structure. So the crusts of neutron stars are one thing that people study a lot. And they call it nuclear pasta because the structure is in the shape of different pastas. So you'll have linguine or, insert other names of pastas. And that's how actual physicists at actual conferences talk about neutron stars and their crust is in terms of pasta.
Yeah, that's very interesting.
Yeah.
So for our listeners, when you go to a nuclear physics department, do not ask for pasta. They may end up giving you some neutron to eat. So be very careful what you're asking for.
Yep.
Now we got to the afterlife. Now let's see, because you said you study these in labs. Now let's get to the place that your expertise come in a lot.
Okay, let's do it.
Now, how do we measure these things in a lab? What kind of processes we go through, and what kind of experiments actually we have to study this kind of, things that happen in a star, actually?
Yep. So I think it's twofold. One is the how, and the other question is the why. So how do we do it? For the most part, we have some beam of particles, and they hit some target, and they produce some particles from there. So maybe, let's say you have a helium beam that's hitting a target made of aluminum, and it produces neutrons, and you can measure those neutrons. That was a specific example, actually. That's what I recently measured. But you might ask yourself, well, why that reaction? Why that beam with that target? And that is where we go to our astronomy friends and we ask them, hey, which ones are important? Which reactions are going on in stars, and which of them matter for your models and for your calculations? And they actually tell us. There was a paper I was recently reading where they listed 36 reactions that were the most important. And so someone like me says, thank you very much. That's what you guys care about. That's what I care about. And so we'll go measure those.
So you said you take a beam and crash it basically with the aluminum.
Basically, yeah.
And then you get the neutrons. Now, maybe our listeners would not know, how do we actually create a beam, that hits aluminum. So how do we do that in a lab? Because I know it's not easy.
No, it's not. It is and it's not. A lot of these things have been figured out by lots of people that came before us. So someone like me doesn't have to go into the lab and physically make the beam or worry about the particle accelerator working. I just worry about my detector, and I tell the engineer, hi, I'd like this beam, please. And he says, okay, here you go. and then, it's my job as the operator to direct that beam, from where it's made to my detector and to my targets. But yeah, so basically you have a beam that in our case at our lab is charged. So it's not neutral, it has some charge to it. And because it has charge, you can direct that beam through magnets and through lenses. And you can also use the accelerator to do just exactly what it's called, to accelerate those particles.
So let's see, how do we accelerate these particles, right? You see, we go through magnetic, we have a lot of magnets, gigantic magnets there, and not the usual fridge level magnets.
No.
They're extremely gigantic magnets depending on the size of the accelerator. And so you have, because you have charge, this magnetic force is applied to them and makes them move. But how do you accelerate this, actually?
So I would be a little bit careful there. So for our accelerator, it's what's called an electrostatic. So it's a tandem. It's actually in the shape of a T. And what we do is we charge this accelerator up to, we can go as high as 4.5 million volts. And we have a beam that is going to go, potentially anywhere, but it's traveling in a straight line, and it has some charge. And we charge the accelerator up to the opposite charge. And as everyone knows, I think, like charges repel, opposite charges attract. And so this charged beam wants to go to this charged accelerator. And as it passes through the accelerator, we start stripping off electrons from the beam. And at that point, the beam has now gone from negatively charged to positively charged. Now you have a positively charged beam inside of a positively charged accelerator, and so now it wants to go the other way. So for ours, we use this two-step process where in the first case, it wants to go towards it, and then now you've changed its polarity or its charge from positive to negative, and now it wants to go right away from it. And then we use the magnets and the lenses to steer it to wherever we want to go.
So in your experiment, your target was aluminum.
Yep.
And then when the positive charges hit from the other side, you start detecting neutrons.
Yep. So we have a helium beam that hits these aluminum targets. You produce neutrons, and you also produce this new nucleus, which maybe I'll not say anything about. But then you have my detector, which has a bunch of detectors around this target. So the target's in the middle, the beam comes in and hits the target, and neutrons are made in every direction. And we have sort of an array of neutron detectors that are around it. And so no matter which way those neutrons go, I have a detector in place. And through my work during my master's thesis, actually, it was my job to figure out how we should put those detectors around these targets. And I ran a bunch of simulations for that and figured out, sort of this best placement.
So for our listeners, just to make them understand, when actually you have this positive charge hitting the aluminum, you get neutrons. So the question would be, why do we get neutrons if a positive charge is hitting aluminum? Okay. Why do we get neutrons? And why don't we know what direction they are going at, to put a detector there, right?
Yeah. So when you have your aluminum element and you have your helium, if you hit those two things with enough energy to pass what's called the Coulomb barrier, you basically have enough energy so that the electrons in the aluminum element and the electrons in that helium, you have enough energy so that they pass through that electron cloud. Now, in your center of both elements, you fuse together and you create something that we call the compound nucleus, which just means the thing that those two together makes. And from there, it's actually dictated by nature. So you can't destroy energy or create energy. You also can't destroy charge or make charge. And so this compound nucleus is going to decay, and it has to decay in a certain way that is allowable by just the governing bodies that made the universe, let's say. And so it turns out that for the most part, you end up emitting a neutron, and you are resulted with a phosphorus 30 element.
To conserve the charge, right? The charge of the system.
Exactly. Yeah, you also have to conserve the number of protons, the number of neutrons. That's called baryon conservation. Charge conservation is the other thing that you have to worry about. You have to conserve energy, you have to conserve momentum, and it turns out that that's just the way that the universe works. And so we can predict what will be made.
And then why do these neutrons are not, you can't actually know where they're going to go, which direction they're going to move in after the interaction?
So you can for certain reactions. We refer to that as an angular distribution, which just means in which angle is the neutron going to go. And there are theories that will predict that. But for my detector specifically, we're doing reactions where we don't necessarily know what distribution of energies we're going to get or which distribution of angles we're going to get. So it was my job to design the detector to work regardless of what angle the neutrons come out and what energy they come out. And there are a lot of these, they're called long counters. Basically, it's just this kind of big plastic box that we put neutron detectors inside. And there are a lot of these, I would say, on the market. But some of these detectors didn't account for the fact that you're going to be getting neutrons of not all energies, but a large range of neutron energies. And they didn't necessarily account for that. So my advisor, when he started up his research group just a couple of years ago, decided that he was going to have a detector that was primed for this specific task. And so that's where my simulations came in to figure out, okay, exactly how we should do this so that no matter the angle, no matter the energy, we're going to treat all neutrons the same, which is kind of funny to put it that way, but that's basically what we're doing. We don't care if you're 5 million electron volts or you're 10 million electron volts. We're gonna detect you the same, and that's what makes the detector special. And I've been incredibly excited to go to different conferences and talk about the detector and to hear how excited people are to use it. So that's been really cool.
Because for maybe our listeners would not know, or just to clarify, when you talk about quantum mechanics effects, when neutrons are coming out, it's very probabilistic. You can't have you can have a range, but they can go crazy. So I think that's a very clever way of doing it, to make sure that nothing is kind of hidden from your eyesight when the neutrons are actually coming out. Now, so this specific interaction that you have helium hitting aluminum, what is the importance of that specific experiment to astronomers? Why are they so excited to see this interaction?
So I want to be a little bit careful here. So the aluminum measurement that we did was it is related to astrophysical importance, but not directly to what I've mentioned before. This was a measurement that had been done before and that we could use basically to cross-check what we measure with this new detector to what other people had measured. So, because we're just getting this up and running, we want to stick to things that we know pretty much what the answer should be, and so that we can compare it with what people have done before and say, okay, yes, this detector works, it does do what it's supposed to do. But the first true, I would say, science measurement that we did was with a zirconium target. And it turns out that for this core collapse supernovae, the neutrino-driven wind, these elements that we don't fully understand how they were made or where they were made, the modelers have told us there are a few reactions that are very important. And zirconium-96, we say alpha N, which just means alpha is N, or helium is helium and alpha is the same. Helium N hits zirconia and produces neutrons. How much of the time that you send in those helium atoms do they actually produce neutrons? And that's the number that they need for us. And that's going to allow them to say something about how many elements were created in that core collapse supernovae.
Yeah, so for astronomers, that's important. And the other thing I want to ask is, since we're doing this in lab, right, we don't have access to stars. We can't. Yeah. We haven't even had access to our own sun, which is only 8 light minutes away. How do we try to go to see if the experiments we do in the labs actually relates to what happens, reflects what happens in the stars?
Yeah, that's a good question. So we work, I would say, kind of in a team of 3. So we have the nuclear physicist, you have the astronomer who's doing the observation, and then you have the modelers who are using their computers to develop simulations and models of the stars. And so if someone like me goes out and does an experiment and I say, okay, this should be the answer, let's say. And then they go and they look at the stars and they see, let's say they look at spectral lines, which just means you use your telescope to look at stars, and you'll see, we'll just say different patterns in your results depending on which element you see. And if my reaction says that they should see this spectral line and they don't, well, then they're going to come back to me and say, okay, this couldn't be right. And then I might go back to the modelers and say, okay, well, you told me that this should be like this. And so the 3 of us sort of all work together, constantly checking ourselves and constantly checking each other. And we also have multiple people doing the same thing, which I think is really important. So, I mentioned that there are several detectors similar to the one that we're designing, or that we've made here at OU. We're not the only ones that are going to do that zirconium measurement. We're not the only ones who have done it. There have been several people. So through different labs at different times, and different observers and different modelers, we all sort of check each other and hopefully in the end come to the right answer.
Yeah, so this cross-checking is very important because you want to see it's repeatable, right? It's not just a game of chance that this happened. It can be a game of chance, by the way. There has been experiments that were just game of chance. Now, regarding the next question I have is, have you seen anything surprising that actually caught your eye in the lab that made you go like, wow, this is something that I have never seen before, or something that's crazy?
Yeah, I don't think I would say so in maybe the sense that you're asking the question. If I'm to be totally honest, I'm a lonely grad student who, worked for many years just on my computer and sort of made this prediction that this detector should be like this and it should give us this result, let's say. And then we built it, and then we did a measurement with it, and I did my analysis, and I looked at the result that I got, and I compared it to what other people had got before, and they were the same. And if I'm honest, that was kind of shocking to me. I worked so hard and wanted to believe that it was going to work, but then it worked, and it was. It shouldn't have been shocking, right? Maybe I should have more confidence in myself, but if I'm honest, that's how I felt.
Yeah, it is shocking, right? When you do the calculation and you go and you see the results, sometimes it makes you go like, I was actually right.
Yeah.
Being a grad student, usually you're not usually right.
Yeah, I have been wrong a lot.
Yeah. And that's how science works, by the way, right? We are wrong a lot, but at the end of the day, we get it kind of right, but we don't claim it's absolutely right.
Yeah.
So I saw in one of your papers, I don't know if I am mistaken, that it was talking about symmetry, right? Something happened in one of your experiments. You saw the symmetry was violated. Am I correct? Or
so that's an experiment that I took part in. So one of the nice things that we get to do is, as graduate students, is we get to go to other labs and help with their experiments. So that was a reaction that was measured at Michigan State a few years ago, and their paper has come out on that very recently. This was something that I took part in, just taking shifts basically. As a grad student, you get to sit and push start and stop on the computer, but that's not necessarily something that I've been researching myself.
Okay, so just because I wanted to see, I was myself interested to know about it. Now, the research you're doing, as we talked about, is very going to become important for astronomers, right? So what are going to be the implications of these results in astronomers, decision making in the future, or in their research?
Yeah. So it turns out that if something I haven't been totally clear on is the idea for these sort of mid-range elements that maybe they were created in core club supernovae. That turns out to be true only for a few astrophysical conditions. And because these nuclear physics inputs either aren't there, haven't been measured, or they're very uncertain, it prevents them from deciding if that's the case. So as soon as me and the rest of the nuclear physics community makes these measurements, and they're able to put those into their models, they will then be able to change their models, change it for different astrophysical parameters, and hopefully be able to say, yes, these elements were made in core club supernovae, or no, they weren't, or yes, they are, but only for certain conditions. So we're sort of a speed bump in the road. I guess we could say that. And then at that point, they'll continue doing more observations, more things will be measured, and we'll just sort of keep moving like science does.
So basically, the results of the experimental from the labs, nuclear physics labs, these results regarding these interactions, nuclear physics interactions, is going to help astronomers to make sure they are going to the right direction when they are creating models to study, supernovas, or to not miss any of them, basically, if there is a supernova happening.
Yeah, exactly. So in an ideal world, the astrophysicists wouldn't have to worry about these nuclear physics inputs at all. They would develop their models, and they would only change the parameters in their models that have to do with astronomy. So masses of stars, things like that. But basically they would, I imagine kind of cranking a knob. So you're turning up different parameters of astrophysics, and then you would change those parameters until you see in your model what you see in the universe. But right now they can't do that because there are these nuclear physics inputs that are uncertain, and so we want to totally get rid of that problem so that we can just have the two of. We want to get rid of number 3, which is the nuclear physicist,
which is a hard task.
That's not going to happen in my lifetime. Maybe not in my kid's lifetime, because it costs a lot of money to run these experiments. One experiment will take 5 or 6 grad students, several professors. You have to write grant proposals. You have to get the government to say yes and to give us money to do these things. It's a lot, and so I look forward to that in the future, but it's going to be a while.
So just for our listeners, when we talk about these experiments are expensive, how expensive they are?
Millions per hour. It's very expensive, very expensive. And the thing so running the lab takes money. So you have to hire engineers, you have to hire janitorial staff, all of the things just to run the building. But you also have to purchase all of the equipment. You have to pay all of the grad students. And, you can basically think of any experiment has had at least one grad student working on it for 5 to 6 years. So that's paying that grad student for that student lifetime. And then now you've got maybe another experiment that you want to do. Well, okay, you've got to have 1, maybe 2 more grad students working on it, plus the professors, plus the engineers. So it is very costly.
And I'm sure it's very energy consuming.
Yep.
Because when you said one experiment is 4.3 million volts.
Yeah, million electron volts.
Let's translate that to light bulbs. And
light bulbs, like, are they on?
Let's go to watts, right? Let's say in 100 watts. How many watts of energy do you use?
Oh my gosh,
it should be insane. I know
it's insane. I couldn't come up with a number without working it out, but it's insane for sure.
I am sure it is. It would be fine. It would be fun if at the end we did just some number crunching. So people may ask, what is going to be the impact of these kind of research in the future for us? Mm-hmm. Either directly or indirectly. So that's a question I've been seeing asked in the public.
So, on one hand, we want to do these experiments just because we're human beings who want to know things, right? Maybe not everyone looks up into the stars and asks questions, but there's a large percentage of us that do. And so just on a human level, I think it's interesting to study astronomy or maybe biology or anything like that. It's not as directly applicable as some fields, right? Some people don't have to make this pitch because maybe they're studying things that are going to help us cure cancer or something like that. And so when you're talking about astrophysics and nuclear physics in particular, there isn't that direct, we're going to study this and then it's going to have this exact application to society. But in general, personally, I think it's a good idea to have people that are interested in doing science, because you never know what you're going to get out of it. There are lots of technological advances that we've made in the lab that met our purposes that were then translated down into cell phones, for example, or maybe computers. So lots of indirect things that help the general public, for sure.
Yeah, definitely, right? Because the thing, as you said, that's the very important point you made, is you don't know what is coming out of this. Sometimes you discover new physics.
Yep.
That,
And one
go
thing I
ahead.
can say for sure, so it turns out that these reactions that we're interested in for this alpha process in the core pop supernovae, turns out that those reactions that are helpful for these models are also helpful for nuclear security applications and non-proliferation. So when any someone from a foreign country or something like that brings in, let's say through shipping containers, they're bringing in, let's say they're good, they're bringing in whatever they're bringing in. Well, we still want to test those, and so we get out our neutron detectors and we scan their things, and we look at the neutrons that are coming out of their materials, and we can say, okay, there's probably no dangerous material in there, or maybe there is. And it turns out that some of the things that we need to be able to say, is there radioactive material in those containers or not, well, they're the same measurements that haven't been measured, and so we need those. So someone like me goes and does this measurement because I think astronomy is cool, but it turns out they can be used by the government to help prevent people from bringing in hazardous material.
Yeah, so right there, it's just from an experiment. You were talking about studying the interactions that happens in a supernova, which we will never see from close distance, at least in I don't know how many generations. But right away, there is a use case coming out, because there is this wrong understanding that the science fundings for astronomy and all of these fields don't go anywhere. That's a very bad misinformation out in the world. Whatever we have in right now, most of them comes from the foundation that comes from the last century in physics, right? So that's very important point. I just wanted us to talk about it. Now let's go back. We talked about your research, what you're doing. How did you get interested in this, in becoming a nuclear physicist? Did you just wake up one day and said, I want to become a nuclear physicist? Or
yeah, I guess I was a weird kid in some ways, because I always was interested in doing exactly what I'm doing. Every day of my life is a dream come true, because I always wanted to do this. I would watch science shows with my dad, and we would watch the Neil deGrasse Tysons of the early 2000s, and we would watch those shows and ask questions and look at the stars at night, and I just always wondered, and I have a lot of questions about the world and about the universe at large. So for me, I just was just a very curious kid and wanted to study these things.
was it a particular event or something at the beginning, right at the beginning, that hit you that, yeah, I want to become a...
No, I don't think so. I think it was just over time, asking questions and learning more and more about Einstein, for example. I thought he was just the coolest thing ever. I remember I would go to the library and I would get old lectures, and I would come home and I would put them in my CD player and I would listen to them. And like, so it's funny to think that I used to do that, but I was a weird kid. So yeah.
Cool. So when you started physics, right? I think you started at Clemson University.
I did. Yeah, that's where I got my undergrad.
What happened that you got interested in nuclear physics per se, right?
Oh, okay. Yeah. So this is something that I am so thankful that I got to do. When I was a sophomore at Clemson, I applied for an REU, which is a research experience for undergrads. And at that point, I didn't totally know. I think I sort of wanted to do generally astronomy type things. I thought were cool, but I wasn't totally sure. So I applied to this internship and got accepted and got to go to Texas A&M University. And they have a lab similar to ours. Instead of the accelerator is a little bit different. They have cyclotrons. But anyway, I was able to work there for 2 months over the summer, and I lived with other students that were, my age, and we were all studying the same sort of thing. And I got to shadow one of the professors there, and I got to work in their lab. And that's where I learned that you could study astronomy while also doing things in the lab. So at that point, I sort of realized, coding on my computer all day and running simulations wasn't exactly what I wanted to be doing. When I watched those shows as a kid, I didn't realize that most of astronomy is running some codes. Some of it's observation. You could say more about that, but there is the observation component. But for the most part, my interpretation of what you guys do is running some codes, and I wanted to kind of get my hands dirty, and that's how I learned that you could do that.
So just, I'm curious, the first time you walked into a nuclear physics lab and saw those accelerations.
It was Disney World. Like, it was the coolest thing I'd ever seen. Just so cool. The next summer I got to go to the University of California at Davis. And again, it was a nuclear physics lab. They had cyclotrons, and I was just so blown away. And it turns out there's labs all over the country, and with conferences and helping out with different experiments, we get to go and visit some of those. And every time I walk in, and I just think, this is awesome.
Yeah, it is. I the first time I saw your lab, I was also, wow, that is cool.
Yeah.
Now let's switch the gear and talk about if somebody wants to become a scientist, what would be your suggestions if a kid is watching this right now? What should he do?
I would say, as long as you're interested and you want to learn and you want to work hard, that you can 100% do it. The best science we can do is science that incorporates everybody. So we want as many people to be in the lab, or maybe at home writing calculations on their piece of paper. As many people as possible that are interested and want to do this, they should. So from middle school and high school, work hard, get the best grades that you can, try and find some university that you'll like and have hopefully a good time while you're learning and studying. Do as many internships as possible. That's, for me, that's where I learned exactly what my niche was going to be. And just ask questions and, find someone that is doing what you want to be doing, befriend them, and ask them for as much advice as possible. Because if they're already where you want to be, then their advice is probably the best to get.
The one thing I also want to bring in to talk about is there is this stereotype that science is very male-oriented, field, which is insane and crazy when I hear these things. So I wanted to hear your thoughts about this and how can we, if there is something like this, how can we overcome that?
Yeah, I think objectively there are a lot more men that are doing physics than women. Right? I think that's just a fact. But the impression that people have that, I don't really think, I hope anyway, that people aren't saying nowadays like women can't do physics or something like that, because they can. But yeah, I think that there are fewer women that are doing it, but that changes every year. We're getting more and more. And there are different programs, women in physics groups. There are different, graduate organizations that can, help you kind of feel more at home with maybe other women physicists or other male physicists that are, kind of like on the team in some sense, that want to help promote you or make you feel included. So, yeah.
Cool. Now, so as PhD student, usually, from what I remember, one of the professors used to say that one PhD is enough because you learn how to learn, so you can start learning anything on your own because you get confident enough. I want to hear your thoughts on this. So what kind of techniques that you learned that you think if somebody is not doing PhD out there, but they can use these things to learn something better, faster, or I don't know, deeper, let's say.
Yeah.
What would be your suggestions?
Yeah, so with physics, at least from my experience and the people that I've been around, it's almost like we just learned, like you said, how to think critically and also how to troubleshoot. So if I have some problem in the lab, for example, I'm going to isolate the problem. I'm going to think about the different variables that could have gone wrong, test one, and then systematically go through it until I find which one is the problem and then figure out how to move forward. And if my TV is not connecting to my Wi-Fi, well, I'm going to do the exact same thing. And so it helps you, it does just help you think and to troubleshoot different problems.
So just for listeners, right? In physics, when we want to solve a problem, what we do, we bring it to bare minimums first,
Mm-hmm.
and then start complicating because we want to understand what is fundamentally
Yep.
wrong, right? And this comes with practice. Now, as a person who you're doing PhD, how much of this have you seen in your work, and how do you think that can transfer to learning any other skill, right? A person out there in the world trying to learn something, now he's like, how can I do it like a physicist or like a, I don't know, PhD graduate student?
Yeah. Let's see. So you mean in terms of the way that we approach problems, or?
Yes, exactly, right. Because we approach as physicists. I'm a physicist myself, by the
Yeah.
way, right? As physicists, we approach problems very differently. I
Mm-hmm.
would say that's the joke, right? Spherical cow in the vacuum. We start from the spherical cow in the vacuum,
Yeah.
then we start removing the vacuum, adding the air, and make the cow to look
Yes.
normal.
Yes, that is
Right?
definitely
So,
something that we do. Yeah.
what is
So
the benefit of that, right? If anybody else wants to use it in the world,
yeah,
right?
I guess I would say it's, well, I don't know about all of the techniques to solve problems, but I've personally found it's a really good way of doing things because nothing ever seems impossible, especially after you've done a physics homework set. um, so I can figure out, the simplest version of this problem. Okay, sweet, got that. Now let's add some complications to it. Okay, let's figure that out, and then build and build and build, and yeah, I definitely think you can apply that to your life.
Exactly, because the thing is, when you start with very complicated problem, you're just gonna run away from it, right? You're like, this is too
Yep, can't do
hard,
that.
and your brain is stuck because you can't think about anything. But when you start saying, let's go back to bare minimums and fundamentals, it's just as you talked about the TV, right? Let's go there. That's the very good part to talk about. So it's not connecting to your router, right?
Hmm.
Now this is a complex problem. You're talking about TV,
Yeah,
router, internet, Wi-Fi, everything.
yeah,
But as a physicist, how would you look at it? You're gonna say,
yeah. I would say, okay, well, number one, is it on? We're gonna start from the most simple. Okay, is it on? Okay, is my TV on? Yes. Okay. Are all of the lights on that should be? Okay, does my neighbor have Wi-Fi? Are there any outages? So you move from the simple to the complex.
yeah, this is actually very good technique, I would say, that can transfer to anything.
Yeah.
And now this is I think we're getting to the end of the program, but I want to ask you one question. I'm going to ask this from everyone in this channel. What is your favorite book? What book you opened and it made you go, wow, when you finished
Okay.
this book?
Yeah, this would have been a book that I read in, let's see, it was maybe my senior year of high school. It's called Ishmael. It was about a monkey that could talk, and he was giving a critique on humanity. And it opened my mind. And one of the things that I remember the most from the book is that he says they locked up the food, which means instead of humans, creating their own food and just sort of living off the land, now they've locked up the food. So we all have to go to work every day. We all have to, purchase things. And so every day we're all, sort of forced into going to work and doing these sorts of things because they locked up the food. And I don't know why, but I always thought that was so interesting. I guess because most people don't enjoy their work, and we are all just doing it so that we can buy food and buy, clothes and shelter and stuff like that. And throughout my life in physics, I don't ever want to be doing this job just because because I have to feed myself or my family. I want to be doing it because I love it, and because it makes me excited, and it helps me answer these questions that I have about the world. And yeah.
Thank you, Kristyn. I really appreciate it, and I really enjoyed your discussion with you. Hopefully, we'll get you back one more time in the future.
Yeah, I'd love to. This was great. Thank you. This was the first time I've ever been interviewed like this, so I hope it went okay.
It was good. Thank you.
All right, thanks.